Well, I'm sorry, Shon left the room right at this moment.
Wait.
Okay.
We're okay. We're on track. We're doing good.
Okay, good. I probably can go on because what I was going to say is that I'm very thankful to you for you inviting me. The first time I actually had a meeting with Shon was exactly 18 years ago at Reno. There's quite a contrast. I've always been afraid to go to Reno because that day when I flew in, it was 15 degrees below 0 Fahrenheit or 6 degrees below 0 centigrade. And this meeting is somewhat like that first meeting with Shon because I met him at a champagne breakfast at Reno, and that's how we started our relationship. I'm going to be talking about some of the work we're doing in real time. Real time, we're just getting started, and it's kind of exciting. That's why I put it first, but it's also very quick, so there's not much on this. Really, I probably should have went before Jean because I want to give just a little bit of an overview of rotorcraft noise. I know most of you don't work in rotorcraft. I'll keep it at a light level. Talk about the maneuver noise predictions we've been working on for the last few years, and I'm very happy Guillaume Perez now working on Aero, carrying that on there. And then I'll talk a little bit at the end about where real-time noise prediction is going, which is, I think, fascinating. Of course, the rotor environment is very complex. We have the blades are quite flexible. We have to calculate their elastic response. As you've seen, we have to worry about a vortex impacting the blade. In high-speed flight, we have shock waves on the advancing side. But on the retreating side, we have dynamic stall. The weight from the main rotor can interact with the tail rotor. And you have to do all of these things right to predict the noise. So it's a very complicated problem. Very good job security. Of course, when you look at the spectrum for the rotorcraft noise, we have main rotor tones, tail rotor tones. You have even things like gearboxes. And if you've ridden on a helicopter, you know that can be very annoying inside the helicopter. So there's quite a few things going on. I'm concentrating on main rotor noise right now, but as we look towards maneuver, we have to consider tail rotor and other sources. Now, historically, Gutten and Ernsthaus and Deming started working on propellers early. In the 60s, early 60s, the importance of unsteady loading was recognized. Most of the main mechanisms were proposed in the 50s, although the names have changed somewhat. But really, there was a dividing line here in what we were able to do and the level. It was mostly experimental with some theoretical work. But in 1969, when Ffowcs-Williams-Hawkins equation came out, I really think that's been a watershed and gave us the tools that we needed. However, Fairsat and others started the rotor noise theory at that time following Ffowcs-Williams, but the computer power was quite limited back then. And we didn't have a very good idea of blade loading. Instrumentation was also not nearly as advanced as now. In the 1980s, when I started getting involved, there was quite a bit of code development. In the US, there was the NR squared, the NASA rotorcraft noise reduction program sponsored by the AHS and the industry. A lot of industry people got involved. Joshi, I think, you were involved in that program probably, right? At Bell at the time. In the 90s, well, about 1988, Fairsat and Myers published the Kirchhoff formulation for moving surfaces. And by the way, I don't want to forget to mention, Ferry sends his regards. He very much regretted being at this meeting, but many of you might not know he just had surgery, a cancer in the mouth. I got an email this morning from him that he's doing well, and he's grown a mustache and sideburns. But anyway, so from about 1988 till about 1998, the Kirchhoff formulation was very popular, and now it's dead for rotorcraft, in my opinion, because we've replaced it with the permeable surface Ffowcs-Williams-Hawkins equation, which you've heard about. The main point of showing you this is, I think, is very important. 35 years later, the Ffowcs-Williams-Hawkins equation is still the most important tool for discrete frequency noise prediction in rotorcraft. This is after 10 years or more of CAA. This is true, and you've seen it in all the presentations, that Ffowcs-Williams-Hawkins is still very important. And in fact, we're using it to do things it was never intended to do, I think. We're beginning to calculate true broadband noise, trailing edge noise, literally any kind of noise source. I think that's a real tribute to the equation. This is one form of it, the way that Ffowcs writes it. For those of you who don't know, I was at NASA Langley for many years under Ffowcs' guidance. It was actually Jay Harden, though, that suggested I go study with Shon. And it's the Fox-Williams-Hawkins, as you'll know, is a rearrangement of Navier-Stokes. That's the most general form, I think, of the light-hill acoustic analogy. The monopole term represents thickness noise, the dipole loading noise, and we still have a quadrupole term if you use the actual blade surface for the surface. If you have a permeable surface, there's no real physical meaning, and as Shon taught me, you can rearrange these sources in all sorts of different ways, so you shouldn't get too attached to them. I think of them as mathematical sources, not physical sources generally. When we're using these terms, we have several approaches we could use. The acoustic analogy, well, we could integrate over the surface and over the whole volume, and that would be, we should get an exact solution. In fact, we've done that for helicopter rotors in high-speed situations. Typically what we do, though, is we neglect the quadrupole term because integrating over the volume is difficult. Even today, getting that volume data accurately, time-dependent, is difficult. So we typically neglect the quadrupole and just do a surface integration. Now, the Kirchhoff formulation was attractive, and why it gained such popularity is because CFD could provide unsteady data on a surface. A surface integration is much simpler and computationally efficient. The Kirchhoff formula was based upon the wave equation, though, not Navier-Stokes and conservation of mass. What we've shown a few years ago was it's really inappropriate for most rotor noise prediction, not because there's anything wrong with the equation, it's because the input data that we use is not suitable. It contains fluctuations in pressure and velocity that are not a solution to the wave equation. But the Kirchhoff formula doesn't know that. If you put the wrong data in, you'll get the wrong answer out. And that's what we've been able to show. So Fox-Williams-Hawkins equation, on the other hand, is essentially the same amount of work, very similar input data, but it's based upon Navier-Stokes equations, and we don't have that problem. Another thing we could do is direct computation, but that, for a long time, will be limited to the relatively near field, and it's needed to provide input data to the other approaches. So what have we been working on the last few years is maneuvering flight. How is that different? Why is it a separate problem? Well, first of all, in a helicopter already we have blade motions, the rotation, flapping. If you're a helicopter guy, you have to do this at some point. You have the pitching, all these things going on. Well, now in maneuvering flight, you have the pitch roll, you have the aircraft, and you can have transients. The time scales are much longer. For periodic motion, it's one blade passage, an order of milliseconds. Maneuvering flight, it's the whole maneuver you have to calculate, so computation becomes an issue. The loads for each blade are no longer the same as they are in periodic flight, and the motions are different. And there's an increased possibility of interacting with the rotor wave, as John has already shown us. In the past, there's been very little work done on predicting maneuvering flight or even measuring it. Most of it's been done in the last 5 years. Just a simple example, and this is without blade vortex interaction noise included. One of the first things we did, just to show you, if we look at the overall sound pressure level on the ground for a helicopter doing a left turn, a level flight, or a right turn, you can see that we get more noise in the turns and it's not symmetric because the helicopter is not symmetric. So we have this kind of thing we get right away. What I've been interested in primarily, because we were one of the few people that could do it, is looking at the noise in transient maneuvers, what I call transient maneuvers. For example, one of the first one we considered, and it was probably a poor case for the capability that we had, is a helicopter in descent where we would increase the collective pitch, increase the angle of attack on all the blades simultaneously to stop the descent. Essentially, the rotor would produce more thrust. Here you can see the collective pitch. At half a second, it was increased by 6 degrees, and then by 1.5 seconds, it was back down. And what happened is the aircraft pitches up. It yaws a bit because we didn't include tail rotor or pedal to stop the yaw as it produces more thrust, more torque. And we actually fixed the roll degree of freedom in our calculation for simplicity. It's one of the first calculations. And for an observer that was initially underneath the helicopter, you can see of the helicopter in steady descent, this is acoustic pressure versus time. The green line is steady descent. The red line is the increased noise that we get during a transient descent. So we get 3 to 4 times the amplitude of the acoustic signal over this short duration. This is without including the wake and blade vortex interaction, which is quite important. So in a transient, we can get a big increase in noise, and that's been neglected through all the years. When we look at the contours on the ground, this is the Y direction, X direction at different times, as indicated. This is the top row is a steady descent. The bottom is a transient or arrested descent, pull up. And this black circle represents where the helicopter rotor projects onto the ground plane. And you can see essentially in a steady descent, it's just moving, the pattern's moving along. It's getting a little closer to the ground, but only about 6 feet. In the transient case, you can see a large increase in amplitude on the order of probably 6 to 8 dB, maybe more. And that doesn't include blade vortex interaction. So what we did is we teamed with the University of Maryland, and we coupled with a flight simulation code called GenHel. This is actually used by Sikorsky. They developed this particular version for NASA Ames, and they use it in flight simulators. The pilots are studying the flight dynamics of the aircraft. We took the aircraft motion and blade motion from GenHel, gave that to the University of Maryland, Gordon Leishman and his students. They have a maneuvering wake code. They calculated using a free wake the blade loading and the motion of the blades, the flapping motion. We put that back into our code PSU WAPWA. We also could go directly, and then we could calculate the maneuver noise with BVI. So this was it's our first attempt really to include all the effects. It's much like what they're doing it on Aero. We did a slightly different case, almost the same. Again, it's a descent with a pull-up. We include the collective pitch like that. And then the thrust on the rotor, you can see increases. So we expect the noise to go up due to thrust. It turns out it goes up more than just the increase in thrust. I'll show you plots of the loading on the rotor disc. This is the 0 degrees azimuth, this line. This is the tail of the helicopter. The blades go around in a counterclockwise direction. And what I'm plotting is normal force versus radius. So for one blade as it goes around. And this is the first revolution, second, third, etc. And so what you can see is during the arrested descent, initially there's a rapid variation over here on the retreating side of the rotor. That's retreating side BVI noise. The vortexes from the tip is coming close here. As we go into the maneuver and start to do a pull-up, we start getting this variation over here. These are where the individual vortices are happening, advancing side BVI. It becomes very strong right here. And as the blade goes past from negative to positive loading, that rapid change in loading is what creates the highly directional BVI noise. At the end of the maneuver, we're almost back to the initial conditions. I haven't shown the whole thing here. Now, if we look at one observer location on the ground, again, acoustic pressure versus time, what you see with the free wake, these very narrow spikes are the BVI noise. This is an initial calculation. We've got some issues at the very start of the maneuver, even before it starts. There's something going on here that we don't fully understand. I think it might be numerical. But if you look, there's an underlying pattern that agrees with the simulation that doesn't have the wake. And then you have the BVI. And the BVI, it does increase, but it doesn't increase exactly the same way. And we think it's quite likely that BVI may turn on and turn off during a maneuver if you're flying into the wake or other things. That's something we really want to study because it's obviously important. If we look at the animation, and you can't, the helicopter's going here, I'll play this a couple of times, or try to at least. Let's see. It starts out with retreating side, advancing side BVI, and goes back. Okay, now I want to go forward. Let's see if I can do that. Here is the time history as we go around, and I think this is, I don't remember why there's two rows right now, but essentially you can see the same case. Retreating side BVI from the retreating side propagates normal to the blade. As you go in time, you'll get advancing side BVI, a couple of distinct ones, and then later on it comes back more to retreating side BVI. I think this is probably thickness and loading noise, but I don't remember at the moment. Then we've looked at more complex maneuver, this case again without the BVI or the wake included. I need to start this. We looked at them. I hope this will run. Oh well. I'll show you some other plots of this, but essentially we looked at a maneuver where we start in level flight. We do a climb up about 100 feet. Then we stop the climb, level flight again, go into a 90 degree or 180 degree bank turn and out. And I'll try one more time. Oh well. Very nice animation. I'll show it to you some other time. But it's quite interesting. In the animation, we can see every time it changes the flight state, you get large radiation of waves going out. So like when you turn into start the turn, that transient is very important. You can see it here. I've plotted on the left axis the normal force of the rotor. And then on the right axis, the overall sound pressure level due to thickness noise or due to loading noise. So the blue line is the rotor, no, the green line is the rotor normal force. So as it gets to the top of the climb, you can see then the loading on the rotor goes down. As you start in the turn, it goes down and back up. These different events going on. What I want to point out is if you look at either of the noise sources, there's some correlation, rough correlation, but it's not very clear what's going on. It's certainly not related to the overall rotor loading. If we in fact look at observers moving with the helicopter, so they're on a surface fix, when we look at the thickness and loading noise, we see two events popping out. And what those are is in fact when we enter the turn and when we exit the turn. For this particular maneuver, these events, if you look at the total noise, can be variations of up to 10 or more dB, which are very significant over a short period of time. And that's because we're now following the helicopter, the observer. There's no change in distance any longer. There's no change in orientation to the helicopter. Hopefully these animations will work. Okay. I did load them. I did even test them earlier. What's that? I certainly did that. Let me see if I can. No, they're actually in the presentation even. Oh well. Well, as usual, I have a backup. I'll just show you some isolated observer points. In this case, what we looked at, you can actually see what's happening. There's the thickness noise, if I showed you those plots. Essentially, the pattern varies. If I look at a sphere following the helicopter, the pattern shifts around, but the amplitude doesn't change. The loading noise, however, the amplitude goes way up for a moment and then goes back down. So there's different mechanisms going on in this transient noise. It's quite interesting. And we wanted to understand that. So we looked at a single observer again with overall sound pressure level for thickness and loading noise. And since we're doing computations, we could do fictitious maneuvers. What we would do is take in this case, the blade motion from steady level flight. just the rotor blades, the flapping motion primarily, and do everything else from the maneuver. So the aircraft's moving around, but the blades are moving like they're in level flight. And essentially, there's no difference, or very little difference, in both thickness and loading noise. The loading noise shouldn't change, other than the position of the blades are slightly different. Then we fix the roll motion of the aircraft. So the aircraft's banking into a turn, but instead of letting the aircraft roll like it should, we stop that. It just goes around level. The roll motion had a very strong impact on the thickness noise. So the fact that the aircraft's rolling, it changes the velocities, changes the thickness noise. Not too much change in the loading noise. Then if we took the fixed blade loading, so in fact we looked at the loading on the rotor blades that they would have in steady level flight, and let all of the aircraft motions be the same as in the maneuver, the turn. And we see quite a bit of this peak is essentially gone. We still have some change in the loading noise because of the motion, but that peak. So in fact, the loading that's going on in the helicopter, that transient loading accounts for a significant increase in the noise. And if I could never show you the animations, that would be good. Now, we also looked at the duration of the transient. This is actually fairly obvious, but it's nice to be able to show it. If we turn very quickly, the noise increases. That's the green line. We turn in half a second, the roll. If we turn 1 second, that's what I showed you before, and this is 2 different microphone locations, or cheating side, advancing side, again, thickness and loading noise. If we turn very slowly, over a 5-second duration, essentially you can eliminate all that noise. So, in a civil application, you want to make nice, gentle maneuvers. Very true. Good. Military applications, that might not be possible. You might not want to turn very slowly in enemy territory. So, what about real time? That was the first thing in the talk. Why did I talk about real-time noise prediction? Well, one thing that happened is when I went to Penn State, started working on maneuver noise. I was working with Guillaume Perez and Guillaume Brez students, and we really analyzed the numerics in great detail. We looked at even counting operations between different algorithms to see which was most efficient for different problems. And for maneuver noise, we chose a forward time type of thing, like you're using it on Aero. And the results were that the calculations were very fast. In fact, to do real-time noise prediction, what we're talking about is we'd like to be able to predict the noise as it occurs so we could use it in a flight simulation. Effectively, we would like to be able to have a pilot in the loop, and as he flies it, we could predict the noise at least at one observer location. And it's still a first principles kind of prediction. We're not trying to make a lot of approximations on the way. I think this is actually amazing that we can even think about this. Why would we want to do that? I think after we found out we think we can do it, the why comes up. Well, first of all, just if you're doing normal calculations, a fast turnaround time would be advantageous. That way we can do all these observer positions for contours. But we want to also do pilot in the loop simulations. That way we can think of having the pilot fly in such a way to be quieter. Another thing that I think will be very exciting is if we can in fact do real-time noise prediction, we can put a few sensors on the rotor blade to get the loading, and then we can actually have optimization where the flight controller can give the pilot cueing signals to make sure he's flying quietly. Is it possible? Well, almost. I'm going to show you where we're at. We're actually starting this year a project on this. For our test case I showed you with the 80-second maneuver, we did that calculation on a single processor, fairly high speed, but not the fastest anymore, a 3.4 gigahertz Pentium 4 processor. The GenHel, the flight simulation calculation, for 80-second maneuver now takes 1.85 seconds total. And it, of course, is real time. This is usually 20 radio segments for each rotor blade with 4-degree azimuthal resolution. Not quite enough for BVI, but not too far away. PSU Wap takes 44.5 seconds, about half of the total 80. We're using a surface for thickness noise that's 10 by 10 grid on the upper and lower surface. Very sufficient resolution for that. 15-degree azimuthal resolution, but for thickness noise, that's fine. We're using 20 radio segments for loading, 4-degree resolutions, and that's nearly enough for BBI. So we can use sufficient resolution on today's computer with a single processor. What we're in the process of doing is reorganizing the code so that we can do that. So real-time appears feasible today with first principles noise prediction. We are using a compact chord-wise loading model. That's the one approximation we have to get this fast loading time. But thickness shows you that we're pretty close even without that. Now our application is we're developing a flight simulator for rotorcraft at Penn State for education and research to look at flight dynamics, flight control design and cueing system. But one thing that's unique, I think, is that we have acoustics. We spent less than $45,000 on the cost of this, most of it off-the-shelf components, and it's designed for flexibility and ease of use. We want to minimize training time because we have a high turnover in an academic setting. The heart of this is the flight simulation program. We've developed a user interface using MATLAB. These are actually on Windows, but we can do them on Linux. We have plans to couple this with a more sophisticated weight code. PSU WAP is here. It's on a Linux machine. We have a network. Flight Gear is actually a gaming software code that's open source on the web. We have several graphic displays. We call this whole setup a graphical cluster. The pilot here and controls these different codes. I'll show you a picture of our flight simulator. We have 3 42-inch plasma displays. We chose those because they're quite bright. It's very vivid sitting in it. We have 4 LCD panels that we use for the instrumentation panels, and we also have an operator station. We have a seat and control stick. But unlike other flight simulators, we have a couple of very big subwoofers, and we can really shake the whole lab up with those. You have to have that for rotor noise because the frequency content's quite low. This is someone flying it. I was going to bring the flight simulator on my laptop because we could actually fly it, but I'm not very good and I didn't want to bring a joystick along. But this is an example, and this is one more animation, probably won't work either. Is the sound turned up back there? This is a picture of what it looks like, an actual flight. We're missing the high frequency and tail rotor noise. But as the helicopter flies, it's much better on the flight simulator. This computer's a bit slow. We took this to the American Helicopter Society forum and have pilots flying it. And what we can do at this point is the pilot would fly a maneuver like this. In about 60 seconds, we could calculate the sound and play it back, viewing the helicopter from the observer position. So we're almost real time now. Hopefully, in 6 months or so, we'll actually be able to do it as you're flying. And then I'd have to bring the whole kit. So, in summary about rotor noise, I could skip some of this because Shon has gone through some of it. Rotor noise prediction capability is quite advanced. But I think that maneuver is not only groundbreaking, I think it's really important because in real helicopters always maneuver. That's the whole utility of a helicopter. And aside from that, we have gusts and other things. So they're never in steady state flight. The Fox-Williams-Hawking equation really, the title of the paper was Sources in Arbitrary Motion. We're really doing that to a very large degree. And real-time noise prediction is very exciting, and the students love working on that. I have to beat them away because they all want to do it ahead of time before we get paid for it. So I'll be happy to answer any questions. Oh, I do want to comment about this figure. I have had the great privilege of actually being present now twice when Shon made discoveries, some of his greatest discoveries. In fact, this is one of them. You probably don't remember this, do you? This picture I took while I was at Cambridge, and this discovery was he actually figured out how to use, for the very first time, his fax machine. He was extremely excited, and so I have this picture on my wall. Last week, we had the second great discovery. He discovered the tiger. No one else has shown it so far, so we have to show. I'm not sure if he was actually the first to see it, but I'll give him credit at this point, just because the meeting's in honor of him. Okay.
Any questions?
Oh, I love that.